Hello, everyone. We're team number one, Amped Up, presenting Turtles, which stands for Traveling Universal Robotic Tire Loss Evasion Swarm, presented by Nicole, Brittany, Brandon, and Fraz. Tire punctures puts the risk of millions of lives in harm's way on major roadways. We've developed a robotic tire puncture team that can be utilized in any environment. When a tire puncture happens, multiple issues arise, from safety or the inability to change a tire. The tire robot swarm seeks a way to minimize or eliminate that risk altogether. Our direct customers range from elderly passengers to those unable to leave their vehicle. Many of our indirect customers will be emergency personnel or roadside relief groups like AAA. Our design has requirements that range from repairing a tire, locating that puncture, filling the tire, shall be 1.5 feet long, powered wirelessly, have roadside illumination, completed within 20 minutes, weigh collectively less than 25 pounds. Taking care of these robots starts with Nicole at the Identify robot, Fraz with the removal robot, Brandon with the patcher robot, and Brittany with the inflation robot.
Hello, my name's Nicole, and I will be talking about the Identifier robot. Here we see the original and final designs along with their elements. One thing that was changed was the tool at the end of the arm, as well as adding a DC motor for the hydraulic pump. Here's the CAD model in 3 different views. We see the Arduinos, breadboards, and 9-volt batteries. We see the motors that control each of the wheels, as well as the base, hydraulics, and arm movements. A photoresistor that controls the LEDs, a motor that controls the spray nozzle, a camera, and distance sensors. It uses a master-servant relationship. I will talk about the master circuit next. The master circuit controls the wheel movements, along with a distance sensor, photoresistor, LEDs, camera, and spray nozzle. It is powered by a 9-volt battery. The servant circuit controls the movement of the arms and the base. It has a distance sensor and is powered by a 9-volt battery. After it receives the start input, it waits for the input to tell it which tire to go to. After that, it senses if it's light or dark out and turns the LEDs on accordingly, and the camera. Then it proceeds to the tire, avoiding obstacles along the way. Once it reaches the tire, it scans and sprays a solution to identify a puncture. After it has identified a puncture, it relays that information to the other robots and returns back to the starting point and turns everything off. Now I will talk about the code behind this. So I'm just going to go over the code really quickly. Here's kind of where we're initializing the master circuit pins, and then we're starting the loop here and starting up the robot, asking which direction the tire is at so that we can navigate there. These are general movements like stopping, going forward, moving left and right. This will control the LEDs and the camera, the distance sensor, and spraying the solution, generating random tire puncture, and then we move on to the servant Arduino, which will take in different task numbers from the first Arduino depending on where it is in the progress. This one controls the arm movements and the hydraulics. Now I'm going to go over the circuit simulation. It waits to start the mission and which tire it should navigate to. It'll avoid obstacles along the way. Once it reaches the tire, it'll send a task code to the servant circuit to start moving the arm and the base, and then it'll scan. The master circuit will scan and spray a solution around the tire to find a puncture site. Once it does, it'll relay that info to the other robots, return to the start, and turn everything off. Now I'm going to pass it on to Fraz to talk about the removal robot.
Hi, it's Fraz backing in to share the removal robot mechanical design. From the 2D view shows as follows: as 5 servo robot with 5 servo motors with 2 at the top and 3 throughout the arm, a camera for manual control, a case for LED lighting, Bluetooth infrared housing, and in internal you'll see the 2 breadboards and 2 Arduinos. 2 hobby motors will power the robot towards the bottom. Now in the subsequent slide you'll see an interior right view of the robot color-coded arm. You'll also see a thick threaded tire on a spring-based chassis. From the left top view you'll see the exposed servo motors. In the robot arm circuit, you'll see an infrared sensor to receive coordinated data. You'll see an LED lighting for illumination attached to the resistor, 5 potentiometers on the breadboard, a 9-volt powering the arm with 5 servos driving the movement. In the robot motor circuit, you'll see the infrared sensors and the ultrasonic distance sensor to mitigate collision. We've also changed to 2 hobby motors, followed by a 9-volt battery breadboard, an L293D bridge, a potentiometer, and an Arduino Uno. Now, as you can see in the flowchart, we'll receive data input from the identifier robot, and we'll start exiting the container. Then we'll move to the punctured location, and then once at the tire, the robot will check the markings and remove the object. Then return to the start position and the stop signal so the next robot, the patcher robot, can continue. Now, for the coding for the arm circuit, I've defined each servo with a letter A through E. Then I have put a print line to designate the X and Y coordinate from the identifier robot. I'll start off with a void setup to initialize the interface, then an explanation of the alphanumeric designation. Then to continue, I have a void loop for each servo to end the coding for this arm. Finally, for the motor circuit, I have a void setup and a void loop, which designates the direction of the front, back, left, and right. Then I have a void function for each movement, finally the distance sensor at the end. The remover arm cat. Data is received from the identified robot, which designates an X and Y coordinate by an infrared Bluetooth interface. Then the 5 servos will move according to this data. The A and B servos represent the X and Y planar movement. Each letter, A through E, represents its servo, which can move 0 to 180 degrees, which is designated by a subsequent number. Finally, this is transmitted to the infrared Bluetooth hub. The remover motor CAD receives coordinates of the location of the punctured tire from the identified robot. The robot will then proceed to the said location by asking if it shall move forward, backwards, pivot right, or left, designated accordingly by F, B, L, or R. An ultrasonic sensor will also help mitigate collisions. All final data will be then transmitted by infrared Bluetooth hub. Now on to you, Brandon. Thank you.
Hello, my name is Brandon, and I'll be going over the design for the Patcher robot. Here we have the final proposed design for the robot with a few of the parts labeled. There are some additions to this design that I'll go over shortly. Shown here are 2 views of the CAD model for the robot. You can see some of the inside, such as the Arduino board, breadboard, battery, lights, sensors, and actuators. On the bottom left, I've zoomed in on some of the servos for the outer part of the arm, and the picture next to that is a representation of a hydraulic reservoir. Now we'll move on to the circuit of the robot. In this circuit for sensors, you can see we have 3 distance sensors at the top and a photoresistor attached to the breadboard. For actuators, there are 6 servos and 2 DC motors. A DC motor was added to the original design to represent a hydraulic pump, and a servo was added to better control the movement of the arm. The other electrical components include the L293D bridge, 2 LEDs red and green, and 3 resistors attached to the breadboard. Lastly, we're using a 9-volt battery to power the components. Next, we'll go over the flowchart and coding portion of the design. Here's the flowchart showing the inputs and outputs for the robot. The inputs include the start command and puncture location received from the identifier and removal robots, as well as obstacle detection from the distance sensors. The outputs are the collision avoidance responses and the command to the inflation robot once the patching task is complete. Now I'll show a few snippets of the Arduino code to get the robot to perform its task. Shown on the left is the definition portion of the code, and to the right is the setup portion. Next we have the loop function and the information received from other robots. Here's the function for the patcher robot to move to the front left tire, and the function for the robot to complete its patch job. Lastly, this avoidance function on the bottom is executed when there's an obstacle detected en route to the tire. Now I'll demonstrate through a video how the robot works. The robot first receives information as shown in the serial monitor window, then starts its motor attached to the back wheels and navigates to the tire. Once arriving at the tire, the second DC motor representing the hydraulic pump starts and different servos activate to start moving the arm into position. The robot first inserts a rubber stopper, then finishes the repair with sealing compound. After the tire is repaired, the robot returns to its starting position. I'll hand it over to Brittany next to present the inflation robot.
So my robot is the inflation robot. Its mechanical design is to navigate to each of the car's tires to check the pressure. If the pressure is low, then it sends its location to the rest of the swarm. It will then go into standby mode until the patcher is done. Once it receives a go from the patcher, it refills the air and lets the swarm know the job is complete. The key features of my design are the caterpillar tires and the extended joints that allow it to move from the prone position to the upright position. This establishes a more compact design without restricting any functionality. It comes equipped with a distance sensor, mini air compressor, PSI gauge fingers, along with a force sensor, 2 LEDs, 4 servo motors for leg and arm directional movement, a hobby gear motor to drive, a tilt sensor for ankle detection, and 2 Arduinos. And here we get to see all the electrical components that I just went over. The top one controls the top half, the bottom controls the bottom half except for the force sensor, and these 2 will theoretically communicate through Bluetooth. Okay, here's my code. Really not much to say here since the demonstration will show what it does. Alright, flowchart. So it starts, it will then navigate to the back right tire. It checks if the pressure is low. If it is, then it tells the swarm which one's low and goes into standby mode. If it's not, then it will move to the back or front right tire. Once it's in standby mode, it's going to wait for the signal from the patcher to see if it's done. If it's not, it continues to stay in standby mode until it receives the signal. Once the signal is received, it fills the air back in the tire, and then it tells the swarm the job is complete and to return to start. The rest of the chart is basically the same thing, but with each individual tire. So for the demonstration, I'm going to go over the top half first. And what it does is the servo on the top half automatically will go around the tire's rims until it hits the tire cap. That's offset by the force sensor. That's why I set the force sensor high, so it will offset it. Once it finds the tire cap, it communicates with the bottom Arduino to know if the tire's flat or not. That's going to be shown in the serial monitor. And I type in an input to simulate the Bluetooth communication. Okay. So I have the yes from the bottom half already in the serial. There it goes. Once it receives that signal, it will go into standby mode indicated by the green light there. It just went off. It will then wait for the signal from the patcher robot asking if it's done. It will continuously send out that signal. And I type in no a couple times to simulate that it's not done, it's continuing to stay in standby mode. After a couple times, I finally type in done, showing that the patcher is done. It's time to switch back into task mode. It goes into task mode, and I set it on the delay to simulate the tire being filled back up with air. And once that delay is done, it goes back into standby mode and tells the rest of the swarm that the job is complete. And when it goes back into standby mode, the green light will go off. Right, there it goes, and job is complete. Right now, I show the bottom half functioning. And the bottom half, so the servos will automatically navigate to each of the tires using the distance sensor. It'll stop at that particular tire if the PSI is low, and that's using the force sensor, so that's why I set the force sensor high, so it doesn't offset that immediately. So you can kind of see it using the serial monitor going off a couple times. That it goes to each tire, it'll send a signal out saying which tire it's at. Then there, I slide the force sensor low to indicate that the tire's low, and it shows that the front left is low. Sends that signal out to the identifier robot to do its job. Alright, that's my demonstration. That about wraps up my design and function of the inflation bot. So up next, Nicole will be discussing the swarm's collective behavior.
Now we have the collective behavior flowchart for the robot swarm. This flowchart starts with the inflation robot starting and moving to the first tire. If an obstacle is detected, it will avoid that obstacle. This is true for all the following robots as well. The robot will check each tire to identify the flat. Once it finds the flat, an output is given to the identifier robot to start and move to that tire. This robot will scan different sections of the tire to find the puncture location. Once located, it will output that information to the removal robot and return to the start. The removal robot then proceeds to the tire, removes the object, sends a command to the patcher robot, and returns to base. The patcher robot then proceeds to the tire, patches the hole, sends an output to the inflation robot, and returns to the start. Lastly, the inflation robot will inflate the tire, check the pressure to ensure it's at an appropriate level, and return to the starting position.
Briefly going over the MATLAB code, here we have the setup for everything: the robots, the tires, the road, the obstacles, and the target points. And then we move on to the simulation. The first robot is looking for all of the tires. It doesn't know which tire has a puncture in it. There's a function that randomly generates which tire has the puncture in it. And then the robots after that will go to that target tire and do their job, and then return back to the start. And then the first robot will return back to the start. At the end of this file, we have the functions that help the robots move around and avoid obstacles. Next, I'll show you the MATLAB simulation. Here we are plotting the obstacle points before we start. After that, the first robot goes and checks every tire to see if it's flat, indicating that there could be a puncture site in it. Once it finds a tire that's flat, it'll tell the second robot to start and which tire to go to, and then that will scan the tire, and then once it's done, it'll let the next robot know it's done, and then that will go and remove the puncture object. Once that's done, it'll let the fourth robot know, and that will patch the tire up and return to the start, and then the first robot will inflate the tire and return to the starting point, and the simulation is now done.
On this slide, we have listed the bulk cost of all the components and materials used to build the swarm. Here we have a table that shows the cost of each individual robot as well as the swarm total. We have a profit margin to account for labor costs with a slightly higher percentage for the individual bots. That's because generally when buying in bulk, you should save a little bit of money. After calculating the profit margin, we get the selling price for all the bots, and the swarm total comes out to $570. Now, that sounds like a hefty selling price, but you can't put a price on peace of mind. And also, after doing some research, we found that currently there isn't any robot swarm on the market that performs tire repair. We did find tire changing bots, but none that actually patch and fill. In this presentation, we went over our swarm's overall function as well as the individual aspects. We calculated the costs to make this idea a reality and went over the target demographic for this product and why they need it. So what we've learned over the past couple weeks is this: teamwork is key, especially when it comes to projects of this magnitude. And the only way to make this teamwork effective is through communication, especially when it comes to timelines. Now, if we could go back and do it all again, this is what we change. We would have done a bit more brainstorming on our swarm idea. Not that we don't love our idea and the final designs, but thinking a bit more simplistic would have saved us a lot of time and headache. We also would have budgeted our design and coding time more wisely. All right, that about covers the ins and outs of Turtle's team project. Thank you.